thank you very much for giving us this time slot at IXPUG. This is a presentation on some work that I'm doing with two people in my group, Matthew Cordery and Dahai. All three of us are part of the Intel Center of Excellence at Argonne. So most of our work is done on the Argonne machines and more specifically on Gen 9s from Intel. The title of this talk is a little, non-specific, but it has to do with the use of Intel oneMKL for high performance on Intel GPUs for a specific class of algorithms. Okay, so what is the motivation here? The motivation is, of course, we want to utilize for the class of algorithms I'm going to talk about, we want to utilize the math libraries as much as possible. In particular, what we are after is to rewrite the algorithm as much as possible as a sequence of highly optimized functions. So as a sequence of degems or a sequence of LU factors and solves, that sort of thing. And of course, that's a great way, we think, to introduce some performance portability into the software stack that we are focusing on, in the sense that if we move this to another platform, we would just go ahead and leverage their optimized math libraries. Since the number of functions, math functions we are using, or the functionality we're using is a very small number, we're talking about less than 5 different kinds of things, then this sort of makes it a very easy port from one platform to another, okay? And of course, none of this is all that new. Applications have long introduced layers to easily allow developers to adopt native math libraries on a variety of platforms, okay? So as I mentioned, this is for a particular class of algorithms, right? So one question is, what kinds of algorithms might be particularly well suited to leverage these kinds of approaches, all right? So the kind of problem we are looking at is wave scattering. And it's not necessarily in one field. We're looking at a kernel in this area. And we're looking specifically at reflection transmission, sometimes called transport problems, but let's just say reflection transmission problems. And the form of the kind of formulation we're after is something that could be applied in electromagnetics, quantum mechanics, seismology, and a variety of fields, okay? So how does this all fit? So in 1D, you might think about, some kind of an incident wave here on the left on this barrier. You have a reflected wave and a transmitted wave. And as you can see, there are 3 sections in this picture. There's the left-handed section, there's this middle section with the barrier, and a third section where the transmitted wave emits. Now, this kind of problem is long been known, that it can be written as a sequence of small matrix multiplications, sort of an explicit kind of approach, or a series of inversions. Okay, so in 1D, it's a sequence of small matrix multiplications. And of course, there's a preferred direction, over here that we have introduced, right? It's just along the X direction here. And in 2D and 3D, these sequences of small matrix multiplications become sequences of large matrix multiplications, okay? Now, obviously, there are lots of details that I'm not going to be going into with the formulation, but there is plenty of literature on it, and I'll allude to it. There's a long history of literature on this kind of an approach, and it's been discovered and rediscovered many times, even in the field of parallel computing, and we think it'll be particularly good for GPUs, okay? So as I said, there's a long history of this kind of an approach. The historical inspiration is, of course, from no less than George Gabriel Stokes. In the papers online, you can look at it, where he was looking at the propagation of light through a pile of plates. So if you think of the pile of plates being in the XY direction, flat plates in the XY direction, then Z is the preferred scattering direction, and you can write this as a sequence of a tight loop of a sequence of matrix multipliers. So the idea being, if you can go ahead and move the data to the GPU one time and put this sequence of operators in there, you'll stay on the GPU as much as possible. And of course, that matrix has to be updated on the from iteration to iteration, has to be updated on the GPU as well. Okay. Now the question is, can this be sort of used in more complicated situations? And happily, the answer to that is yes. So here's a non-trivial problem where it can be applied. So if you look at this left-hand side picture, you've got Z, an atom Z, and you've got an XY molecule, and 3 coordinates describe the configuration in, let's say, the body frame of this molecule. You got a big R Z, a little R Z, and an angle between them. And of course, if you were just looking at that configuration, and that RZ gives you that preferred direction, and you can look at a whole sequence of configurations of that atom colliding with this molecule and then going off again back to infinity. And so RZ would be your propagation direction. For those of you who are familiar with transfer matrices and other areas of physics, this is sort of similar in spirit to that, except certainly more numerical and handled with some degree of generality here. And another way to approach this problem would be to look at a slightly more complicated 3-body system, in which case you have the Z plus XY going to an X plus ZY, in other words, a rearrangement or a reaction if you want. And this would be true of both a chemical reaction and a reaction among nucleons. Now over here, the configuration on the right-hand side is more conveniently described as a second set of coordinates. And so taking the approach of having RZ as a preferred direction would be a problem, right? But it turns out that you can, make a simple switch to something that looks like polar coordinates, and it turns out that that row is invariant. So you can use that single row in all arrangements. So this is a non-trivial application of these sort of transfer matrix or propagation kind of ideas. And I mentioned this over here just to indicate that it's not just very simple configurations that can be adapted in this fashion. Now, one of the motivations for looking at this in the first place is, for a very large number of applications that we run into, so I should have mentioned that in this RZ propagation direction, you can use a series of elements, right? And you can think of it from a finite element point of view as well. Now, if you think about a generic finite element code, a lot of folks, they tend to, not all, but a lot that we've run into, go ahead and they construct a large sparse matrix, and then they try to move that over to the GPU to the extent that they can, and do with it what they want to have happen. However, for large enough problems, that's going to be an issue, right? So it makes a lot of sense to reduce the size of the data. And one approach in traditional finite elements is to do an element-wise matrix multiplication. In that sense, you're only moving small amount of data to the GPU. This is in that vein, right? So we have a small number, since we break the larger boundary value problem, by the way, into a series of smaller ones, we'll only be moving a small amount of data at any one time. And so we can do larger problems in the non-propagation direction, right? So anyway, this is a lightning talk, so I will conclude quickly here. A relatively large number of problems, I hope I've indicated that a relatively large number of problems can efficiently be represented as a sequence of these kinds of sequences. We expect this will be useful when we run into limits on how much a GPU can hold, for example. These types of problems are ideally suited to achieve a good degree of performance portability, in the sense that we only going to use, as much as possible anyway, use pre-optimized library type functions. And of course, in that sense, oneMKL is a good choice on a variety of platforms for this kind of approach. With that, I'd like to thank IXPUG again for giving us this time slot, and of course Argonne for providing us with machines and other support and to do this kind of work, and of course for Intel for also supporting it. So thank you. I'll take any questions if there are some on the Slack channel.